So let's confirm. All right. So thank you, everyone, for the 2022 Planetary Defense mini conference, AIAA LALV. And thank you first and foremost for UCLA for hosting us at the UCLA Meteorite Gallery, which is an exciting place to take the family and kids to see what is the nature of those objects that come from space. We're going to hear a series of exciting talks today from actual missions to asteroids by Andy. And we'll hear where we are in that mission today and what to expect in the next months. Then we'll hear from Madhu about breaking news on planetary defense and other topics. And we'll take a break. We'll join in person at the gallery, take a tour of the gallery with the UCLA scientists and professors and hear a few interesting talks. And in the afternoon, we'll cap with a few other talks about science missions to asteroids, STEM education, and so on and so forth. So with that, I will let you start, Andy. Again, thank you very much for everybody that's participating today and looking forward for an exciting Asteroid Day event. Take it away, Andy.
All right, thank you. Thank you for having me, Dr. Melamed, and thank you for having me, members of the AIAA. I always screw that up. So I'm going to talk about the Dart mission today, which is the double asteroid redirection test. I'm going to start out by talking about planetary defense in general, although I suspect most of you have heard this before. And I know I've got a lot to talk about, not a lot of time, so I should just get to it. So every time you go outside and you see a shooting star, you're basically witnessing an impact. It's a very, very tiny impact, but it is an impact from an asteroid or a comet. Something like 100 to 300 tons of material hits the Earth every day on a typical day. And if you go outside to someplace dark and you get yourself dark adapted and there's no bright moon, you can see 5 to 10 of these impacts every hour. The material is only about millimeter sized, maybe 1 or 2 grams of mass coming in, and it never reaches the ground. So this is not at all dangerous. These are the kind of impacts that, of course, people maybe like best. Larger objects do hit the Earth. Every few months to a year or so, something the size of the chair that I'm sitting in hits the Earth. The Earth is big. You don't see them all the time, but in 1992, the fall of 1992, there was such an object that was maybe between chair-sized and couch-sized that entered over the eastern United States. It happened to hit on a Friday night, so a lot of people were out there with their video cameras watching their kids play football and taking videos. And so this animation here in the upper right is such a was taken that night. This is big enough that some pieces can hit the ground. They don't do a lot of damage when they do hit, unless your car happens to be sitting in the wrong place, like this young woman's car, which was struck by a piece about 1 foot in size. It totaled the car, but she made her money back by selling the car to go on parade, to go on a tour of gem and mineral shows. As you get to larger impacts, they occur less and less often. There was an impact of an object about 20 meters in size that occurred in Siberia almost 10 years ago. Again, there's video of that. These come from dashboard cameras that people had, and this impact, blew out windows all through the city, and the broken glass ended up injuring about 1,000 people. So impacts are something that, as they get larger and larger, we start to have to worry more and more about, although they do also happen less and less often. This map here shows where impacts have been seen by US satellites in the past 30 or so years. And as you can see, they can happen anywhere. The Chelyabinsk impact in Siberia that I was talking about, I don't know if you can see my cursor, but that's this one. But there are some others that are maybe not quite as big and energetic, but again, they can occur anywhere. If you look at more quantitatively how often these happen. You know, like I said, something at 4 meters in size, so maybe a big couch, happens once per year. There's hundreds of millions of these objects out there. We found almost none of them, but that's okay because, you know, they just basically give us a nice show when they hit, and they can leave meteorites, and then that's great for folks who take them into the lab, like you're going to be seeing a little later on today. At the biggest end here on this chart, 10 kilometers across, 6 miles, these happen every 100 million to 200 million years or so, we think. But there's only 3 of them out there right now that are in orbits that are vaguely close to Earth. We know that none of them are dangers. They're not going to hit, which is good, because if they did, that's the sort of thing that gives you a you know, mass extinction. That's bad. And as you kind of move toward the middle, you get to this 160 meter size, which I'm going to call out specifically. We've only found about half of these objects. We think there's about 20,000 of them or so. They impact every 25,000 years or so. So that's not very often. But you know, if you're poker players, every decade, if you take that once per 25,000 years, that means once every 2,500 decades. And that's about the same odds of getting a dealt a 4 of a kind in 5-card poker. So basically every decade the universe is dealing us out you know, a hand, and if we get a 4 of a kind, we're going to get hit that decade. It's not common, but sometimes it does happen. So it's the sort of thing that we want to think about. Planetary defense is us thinking about it. It's the field that is addressing this issue, and there are various parts of it, from searching to find what's out there, characterizing what we find, and then mitigating, you know, figuring out what we would do about it if we did find something. The Planetary Defense Coordination Office was established by NASA to do these various pieces. The Dart mission, which I'm going to talk about, is specifically a mitigation mission. There is a national plan to think about near-Earth objects and impacts. And again, one of the pieces here is deflecting and disrupting anything that comes our way. And Dart is a demonstration test of that mission. I'm just going to fly through this. There are 4 techniques that are thought to be mature enough to try right now. Civil defense is basically, as you might think, just kind of go to your basement and hunker down. Nuclear is, again, what you might think. It's using a nuclear device like in the movies. A kinetic impactor, kinetic impactor here in the middle is what Dart is. And it's a very simple concept. You ram the asteroid you're worried about with a spacecraft. You use the momentum of that spacecraft to change the momentum of the asteroid. That changes its orbit so that it would miss the Earth, and then everyone's happy. While the physics is pretty straightforward, we do want a test flight so that we can really understand how it would work if we needed to make it work in practice. Asteroids go around the sun at about 30 kilometers a second, about 20 miles a second. There are reasons that we don't want to change an asteroid's speed by more than a few centimeters per second, a few inches per second at once. We don't want it to fly apart. We want to more or less keep it intact. So to make that sort of change, you either need a separate spacecraft to monitor the system as a whole, because you're only going to change this thing that's moving 6 miles a second to be suddenly moving 5.999999 miles a second, and that's hard to measure. Or we have to come up with something clever, and my colleague Andy Cheng at the Applied Physics Lab did come up with something clever, and that's to visit an binary asteroid system. That's an asteroid that has a moon, and to change the speed and do the test on the moon of the asteroid instead of the main body. So instead of moving around the sun at 6 miles a second, asteroid moons move around asteroids at mainly maybe a foot a second, maybe a couple of feet a second, maybe 6 inches a second. So to change the speed by an inch a second or a fraction of an inch a second is much easier to do. So we formulated this mission to go to an asteroid with a moon. That's the double asteroid in Dart. Here's a quick overview of what the mission is. The last time I gave this talk to you folks, we had not yet launched. We had a great launch. I'll show some pictures of that later on September 26th out of Vandenberg Space Force Base. We are going to arrive at Dimorphos. I'm sorry, we launched November 23rd. What am I saying? November 23rd out of Vandenberg Space Force Base. We arrive September 26th of this year at the asteroid Dimorphos. We're carrying a CubeSat, and then after the impact, we will be making measurements from the Earth to figure out what it is that we did. Dart itself is not a very big spacecraft. It's only about the size of a vending machine. If you count its solar panels, those extend out to be more sort of the size of a bus from one wingtip to the end of the other wingtip. Dimorphos, the asteroid we're going to hit, is about the size of one of the pyramids in Egypt. So people have asked, are we going to destroy the asteroid? Are we going to, disrupt it just by hitting it? And you can imagine, if you fired a vending machine at one of the pyramids of Egypt, you'd wreck the vending machine. You might kind of make a divot in the surface of one of the pyramids, but we're not going to destroy it that way. Also shown here is Didymos, which is the body Dimorphos is orbiting, which is again kind of human scale in the sense that it's not like Jupiter that's immeasurably large. That's very, very hard to wrap your head around. Didymos is, at least in one dimension, only about the size of our tallest skyscrapers. Dart has 4 things it needs to accomplish to be considered a success by NASA, which of course is what we're looking to have happen. It needs to impact Dimorphos and needs to do it this fall. It needs to change the orbit period of Dimorphos around Didymos by at least 73 seconds. We need to measure that period change to a certain precision so that we not only make the change, but we see what we did and measure it. And then we need to measure how the momentum of the Dart spacecraft gets coupled to Dimorphos itself. And this is done by measuring this factor we call beta, which I'm going to talk about more in one of the next couple of slides. In fact, here it is. Basically, beta is a measure of how the Dimorphos's or any asteroid's momentum after a kinetic impact versus before the impact, or how the change in that momentum compares to the momentum brought in by the spacecraft. If you have a very simple, high school physics problem and an inelastic collision, all of the momentum is conserved and beta equals 1. The change in Dimorphos's momentum will just be equal to the momentum brought in by the spacecraft. But we don't think that we're going to have a closed system. We think we're going to make debris. We think that debris is going to carry momentum with it. We think it's mostly going to be in the direction opposite that Dart's incoming direction. So that's going to give an extra push to Dimorphos. Maybe it'll be a factor of 2. There are reasons to think that it could be even bigger. Maybe it's going to be a factor of 4. There are other reasons to think maybe it'll be smaller. Maybe it'll be more like 10%, 1.1, 1.2. This is one of the main unknowns that we're going to try to determine from the Dart experiment. So this is looking down on Earth and Didymos and the Dart orbits from the North Pole of the solar system. There, that shows Dart getting launched. Dart stays actually pretty close to Earth. It moves outside the Earth's orbit, and then it impacts Didymos in September of this year, when Didymos is very close to Earth, close enough that we can use telescopes, that we can use radar from the Earth to make the measurements we need. And we're going to do these measurements not by seeing Didymos and Dimorphos as separate objects, but as one point of light. That point of light will get brighter and dimmer as Dimorphos moves around and throws its shadow on Dimorphos, and as it moves behind Didymos, and is blocked by it. This bottom trace here shows schematically how the brightness changes when Dimorphos moves in front and throws that shadow. And then when it is blocked by Didymos. By measuring this pattern of the brightness going up and down, we can get a very, very good measure of how long it takes for Dimorphos to move around Didymos. And we've been making measurements like this for years and years. I think the first ones in our catalog are from 2003. After the impact, we will make these measurements again, and then we'll compare how often we get these dips after the impact to how often we were getting them before. And that will tell us how much we changed Dimorphos's orbit by. We'll also make simulations or computer simulations of the impact. This very psychedelic looking thing is kind of looking at an impact from the side. So it's a cutaway view. Here's our impactor making a crater. The different colored balls here represent a what we call a rubble pile structure. So lots of boulders and fragments and blocks laying against each other rather than being one monolith. By studying the debris that's thrown out from the actual impact, comparing it to simulations like this, taking simulations like this and saying, okay, what would the momentum transfer be like? How much momentum is being carried by the ejecta and the debris? That will again let us couple the computer models to what actually happened, and then use those computer models in other ways to simulate other situations that we're not actually going to be doing for real. This is shows the Dart spacecraft. Again, the dimensions I talked about there before. These are kind of some of the more important technologies that are being flown. We have the rollout solar arrays. These started out as kind of rolled up like paper towels. I'll show that in a picture. They rolled out pretty early in the mission, and they're working great. LiCiCube is a CubeSat that's built by the Italian Space Agency. I'll talk about that some more. Draco is our one instrument. It's a camera that's based on the LORI camera that's on board the New Horizons mission that went to Pluto. And it's also related to the Lucy LORI camera that's on the Lucy spacecraft. And then the smart nav is the algorithms that will bring us in. Here's I think it's LiCiCube. The LiCiCube folks made this graphic. LiCiCube is only about the size of a cereal box, so it's a typical kind of CubeSat. It also has a cousin that will be flying on the SLS called Argomoon. LiCiCube has two cameras. They're Star Wars fans, so they call them Luke and Leia. One is a monochrome, so just black and white photos, images, I guess not photos technically, and those will be of higher spatial resolution. There's also a color camera called Leia that will have a little bit lower spatial resolution, but again will have the color capability. So LiCiCube will be deployed by Dart about 7 to 10 days ahead of Dart's impact. It'll back off a little bit. It'll move so that it's not on an impact trajectory, and then it will. And then it will arrive and make its closest approach to Didymos about 3 minutes after Dart arrives and impacts, and take images of the aftermath there, at least the immediate aftermath. Since LiCiCube is on a flyby trajectory itself, it doesn't stick around. It keeps going. It stays relatively close to Earth and downlinks its data for several weeks later. So there we go. As I said, we have one instrument. That's the Draco camera. And Draco is going to give us all the information that we don't currently have. Everything so far has been remotely measured, either using light curves. We've been taking images for years. Here's an animation of Didymos moving across a star field, and like I said, we're measuring the brightness go up and down. There's radar data from 2003 from the late lamented Arecibo telescope that gave us a shape model of the main body that Dimorphos is orbiting. And then we have measurements of its composition using visible and near infrared spectroscopy that tell us that Didymos is pretty similar to a specific kind of very common meteorite, an L or an LL chondrite. So it's representative of the kinds of material that is commonly in near Earth space and that commonly hits the Earth. We don't know a whole lot about Dimorphos itself at this point. There are a lot of different shapes that are seen out in the wild as asteroids, and so the team that were working on making sure that we impact Dimorphos, the engineers had to look at a wide variety of possible shapes. The data we have suggests that these two, Eros and Cleopatra, maybe are too extreme, that we don't expect Dimorphos to look like that. While we don't know for sure, we're kind of betting on something more like this here, kind of this KW4b shape. But the tests have been done with all of these shapes to validate the system. The Draco camera has been taking data, but it's not able to see Didymos yet. It's still too far. We expect to get our first images of Didymos from Draco in late August, so coming up soon. We'll be getting continuous ground antenna coverage for the last 10 days of the mission, and in that last day we start to get into our terminal phase 4 hours ahead of the impact, which should be I think at 4:15 p.m. Pacific time. So about noon on that day, we hand over the keys and the steering wheel to the SmartNav algorithm, and let that start to steer, because the Dart spacecraft is coming in so fast. It's coming in at something like 6 kilometers a second, 6.5 kilometers a second, so over 4 miles a second. We don't have someone sitting there with a joystick trying to bring it in, or an Xbox controller, whatever. I'm an Atari, old school Atari. This has to be brought in by autonomous navigation. We don't see Dimorphos itself until only about an hour out, and then at an hour out, it's only a little more than a pixel across. Didymos is only about 6.5 pixels across. So really, we're getting most of the data we need for some of our requirements only in the last few minutes. Didymos is only 100 pixels across 4 minutes out. Even 2 minutes out, Dimorphos is still only 40 pixels across. And it's not until 20 seconds out that we start to get images with the spatial resolution we need to understand the geology of the area on Dimorphos that we hit, to understand whether we're going to hit a rock or not, or a big rock, or a smoother area. So it's going to be a lot of nervous time, and then just a few minutes of really seeing what we're up against. It's at 2 minutes out, the SmartNav stops maneuvering, and we coast the rest of the way in. And so as noted here, given the precision we need, and the length of time and the speed we're coming in at, basically it's like maneuvering, and you stop steering over the Indy 500 and coast all the way in and land in Camden Yards, the Orioles home park. So for the last part here, I'll just go through some slides. I think these are going automatically. So this just shows kind of the process of putting the spacecraft together, installing the ion engines, doing testing. So you can see actually it didn't look that different from a vending machine, at least on the interior. There's the rollout solar arrays getting installed. Here's the camera, the Draco camera getting put on. Then, like I said, in November we launched. So I don't know if you're getting the audio or not. It doesn't really matter so much. But we were told that Vandenberg was a terrible place to watch a launch, that it was always cloudy, but we had great luck. We were watching from up on a ridge. It was a spectacular night launch, and went on the first go, our first try. So that was really great. It was amazing to see. Here it is again for some reason. And then
the job of Falcon 9 was to get
uniquely, perhaps, I can't think of any other planetary missions that did this, because we launched on a SpaceX mission. We had these cameras, and we were able to actually see them, to see Dart off, and there it goes. So that's the last we're going to see of Dart, we think. Unless maybe some telescopes pick it up in its last moments. I guess LeachaCube might get some images of Dart on the way in, but it was really amazing to be able to see this, to see this spacecraft that we've been up right next to in person, to see it go there in space. And once again, there it is. So like I said, the camera is working. This is an image from the Draco camera of M38. It's kind of a not terribly famous star cluster, but it is in the M catalog, and so this shows it's working. Planetary defense is an international issue, and we have a big international team. We also have a European mission that will be following us a few years after we arrive, and that's called Hera. The Dart and Hera missions work very well together. Like I said, we have a lot of overlap on the teams. The Hera mission will show up and basically see in detail what it is that Dart did, and be able to make measurements that Dart and LeachaCube are not able to do. So, for instance, how big of a crater did Dart make? Make better measurements of the mass of Dimorphos. See if any of the debris made it all the way to Didymos or not. See what kind of dust from the impact might still be hanging around. So they're two really, really great missions working together. This is just again a schematic of Hera, supposed to launch in little over 2 years, and then arrive in December of 2026. For those of you that want to see yourself, Didymos should be, if you have a camera, it should be observable with a CCD or a camera with an 8-inch telescope. This is Didymos itself, the whole system. You won't be able to look at it with your eye and see it through an eyepiece. It's just a little bit too faint. But it's kind of in southern skies around the time of the impact itself, but then it starts moving north. So again, if you've got a telescope and you've got a CCD set up, and you feel like watching a dot move across the star field, you should be able to do that with Didymos. There are other ways to other outreach possibilities there. Obviously, we have a website. We have the Planetary Defender campaign where you can show up. I don't know if we had this last year. Go to that website, take a short test, and get your official Dart Planetary Defender certificate you can stick on your wall. There's plenty of action on Twitter, for better or worse, depending on how you feel about Twitter. I have my own personal account, and then of course there's lots of interactions out there on social media for Dart and planetary defense. If you go to our website, you can also find some other things. There's the instructions, I guess, you need. I don't do this, so I don't know, for how you can print a 3D printable model of Dart. There's for legal reasons, I think we have to call it a toy bricks model, as opposed to the most famous company that makes toy bricks. And there's some an AR app you can download. Here's my colleague and partner in crime, Nancy Chabot, our coordination lead, demonstrating at the launch site with Dart right behind her there. So to close here, I'll just show this trailer that shows the launch, shows the kind of the entire mission. Here, there's Dart getting jettisoned. So that was the video we saw. Here are the rollout solar arrays rolling out while we were still in orbit around Earth. And again, those are working great. here's the camera, the Draco camera opening. Here we are. I showed this, so this is looking down from the north pole of the system again. Here's Dart testing the next C ion engine, and then going on its way. Here's LeacherCube getting deployed. So now, obviously we're taking lots of time jumps, and then LeacherCube's solar panels opening up. Here's the Dynamo system, and the Draco camera kind of taking the data to bring us on in. And then there's a discretion shot, so you don't have to see what happens at the end there. So so there you go. This is, I think I should have updated this. I don't think I did. So we again launched last November, and we arrived in September. So I think that's all I've got. So happy to take any questions that are out there.
Thank you, Andy. This is super exciting. Looking forward to September to see the outcome of the mission. And hopefully it will be successful, and we'll know that we can defend our planet from those objects. Are there any questions from the participants?
Yeah, I see there was a question online. I'll handle that one first. Or a question in the Q&A. Can we talk about the ion engine? So the ion engine is it's called the next C ion engine. So it's a different it's kind of an updated, or it's a more modern one, I guess I'd say, than what was flown on Dawn. And the Japanese have their own versions of ion engines, and ion engines are I guess not uncommonly flown on Earth orbiting spacecraft. So some tests were done with NextC, and I am going to let I'll let the results of those tests come out by in the proper channels, with some NASA report or something else. But that's what I can say about the ion engine.
And there is a question for Mike Hatton about the follow-up mission.
Yeah. Okay. So the Hera. So there are a few different possible ways you can look at a follow-up mission. So for Dynamo specifically, Hera will be serving as a follow-up that the Europeans are flying to the same system that will be literally doing follow-up for Dart. For planetary defense in general, there is a search telescope called the Near Earth Object Surveyor that would do the search for what is out there. That is generally expected to be the next NASA planetary defense mission after Dart. It's support. There's a lot of support for the mission happening. It still needs some budget things to work out in its favor to fly on the time that they've been hoping for. And then after that mission, there's just been a report from the National Academies looking at kind of the next decade of planetary science as a whole, and they were advocating, or they were recommending, that a rapid Recon mission happen. So something that would demonstrate, how quickly could you build and fly a reconnaissance mission if you needed to do something very quickly. So I think most, in terms of NASA, mostly we're trying to figure out how to make the telescope, the Surveyor telescope, happen. But there are some thoughts about beyond that. And then the only other thing the other thing that comes to mind, I mean, there's a lot of possibilities. The Chinese have been talking about doing a kinetic impactor demonstration, kind of like Dart, but we don't know. They haven't publicized a lot of what they're thinking. So beyond that statement, it's not clear what they might be considering. And then the Apophis, there's a big Apophis flyby, or the asteroid Apophis will be coming very close to Earth, I guess I'll say, in 2029. And there's a lot of interest in trying to take advantage of that and send missions to that.
Actually, I'll add a piece of information about this, Andy, that in the last Planetary Defense Conference, the Chinese introduced a concept of kinetic impact of an asteroid by using the launch vehicle's upper stage, instead of deploying a payload out of the upper stage like we do today, why not use the whole mass to increase the amount of momentum? So they are definitely making progress on that. And we call it international, and hopefully we will collaborate on defending Earth on those missions. But they definitely, if you would like to hear more about this, go to the Planetary Defense Conference 2021, and we have the recording of the talk and the presentation, so we can see what they are doing, and maybe we can have our own initiatives on that regard. Let's see. So there is a question
great.
here: do the solar arrays change angle?
No, the solar arrays are fixed. So that has implications for, at least I'm 99% they're fixed. 99% sure. So that has implications for where, you know, the antenna and everything has to be set up just so the solar arrays are pointing at the sun, and the antenna can point where it needs to point, and the camera needs to point where it can point. But in a case like this, it was relatively straightforward, right? We knew what we didn't have to plan like for Voyager, right? And say, okay, when are we gonna pass by Europa, and when are we gonna pass by Neptune and all that stuff? We just had the one target. We know we were going to hit it in this one particular way, so we could take advantage of that.
Thank you. And there's another question here, which I actually want to connect with your bio, Andy. So it says, what specific density do you expect of the asteroid surface? And the question is, because of Ryugu samples have 12 times less density as Chondrite meteorites. And looking at your bio here, you are actually working on determining compositions from telescopic measurements. Sounds like it's really right down your alley here to look at those kind of things. And one more angle that I would like to add to that is from your talk, looking at the estimate of beta. I guess estimate of beta relies heavily on characterization of the object, which we seem to be lacking now. So what do we do to be able to have a good estimate on the beta for the benefit of mission design?
Sure, two great questions, and I will take them right, part one and part two here. So Ryugu is, as noted, much less dense than we were expecting. We expect, given the type of meteorite so there are lots of types of chondrite meteorites, right? So there are carbonaceous chondrites, which are low albedo, which are like Bennu and Ryugu both. Both were have much weaker surfaces than we expected. Both are kind of thought to have experienced water, altered by water at some point in their histories. There are also what are called ordinary chondrite meteorites. That's like Eros and Itokawa. Those seem to be stronger. Those we don't think generally did have this experience with water. And for Itokawa, while Hayabusa 2 kind of went in and OSIRIS-REx went in, and instead of touching and bouncing and coming up, kind of went in pretty far to Bennu. When Hayabusa 1 visited Itokawa, it smacked into the surface and bounced around for a while, just because of certain operational things. It didn't sink in very far. We think Didymos is going to be much more similar, and Dimorphos are going to be much more similar to Itokawa compositionally than like Bennu and Ryugu. So that suggests to us the surface density will be more like 2.5 times that of rock, more like 2.5 than like 1. I'm sorry, 2.5 times that of water than 1. Having said that, it's also the case that if it's much less dense and Dart comes in and just buries itself somehow, if it's aerogel or something crazy like that, it still is not going to go all the way through. This is, Dimorphos is big, so In that case, if there is no debris, then it is a perfectly inelastic collision, and beta will be 1. So the momentum is going to be transferred. It's not going to go all the way through, even in the most extreme cases we can think of. As to your question about Dr. Melamed, about what characterization we need, I guess the cop out would be to say the T in Dart is for test, and so we have all of our all the scientists on the team, all of our best interpretations of the current literature of what this asteroid should be like suggests that it should be like the main body. We think that's how asteroid moons are formed. We know what the main body is made of, so we are going to base our estimates on that. If it turns out to be very, very different, then that's going to be a good thing to know, because if this were a real problem, if this were, like they say with the emergency broadcast system, if this were a real emergency, we'd be doing something like this, and we'd still have to be using our best estimates of what the bodies are like. And if it turns out that asteroid moons are very, very different, then that's a good thing to know. And then Hera will tell us a couple years later. So
I guess there's 2 ways to look at those: is design for the average situation and design for the worst case. So
right.
You could, if you don't have reliable information, you can assume worst case and try to design for that.
Right. And something else that we've thought about, as you know, because this comes up in the Planetary Defense Conference exercises all the time, right? The idea of sending in a stream, 3 or 4 or 5 kinetic impactors in a row, and you just kind of once you've gotten the result you want, you don't have the other ones hit. So really just getting any data is going to be important to let us understand how these scenarios work.
Thank you. I think we have a minute for maybe one more question in the chat actually now. Why not dock crewed mission to a small asteroid, attach a thruster, and light the fuse? So like basically create some sort of a slow push on the asteroid over time. Do you have any insight into that?
The most I can think of 2 reasons right away. So one is that asteroids are spinning, and so you either would need to put the thruster at the north or south pole, or only have it on a small fraction of the time when it's pointing the direction you want. So that's one. 2 is that we think a lot of these are just basically flying gravel piles that are held together by gravity. So if you light the thruster and you light the fuse, all you might do is take the one little tiny part of it you're attached to, move that, and just disperse the rest temporarily, and then have it come back together under its own gravity. So that's 2 reasons I can think of.
And the last question here, just a few seconds, if there could be some mid-core corrections for the mission. I think you already have said that you do have some control over the trajectory up until very late in near the impact time.
That's right. It's uses normal kind of normal propulsion, normal targeting up until the last few hours, and then the smart nav system takes over from 4 hours out until 4 minutes out. 4 minutes out, it makes the last correction. 2 minutes out, it cuts the engines, and we just go.
Thank you, Andy. I think with that, this was a super exciting test. I think any test has 2 possible outcomes that is going to tremendously inform us. We all hope that we are going to be successful and say, yeah, we can defend our planet, and let's move on to another more involved test, more complicated test. But if we don't make it, then it's going to be a lesson learned. What do we need to do to actually learn from that and do it right next time? So it's going to be tremendously informing. Can we invite you to give us a talk next year at the same type of event with the outcome from Dart?
Sure, I'd be happy to. And yeah, we expect that on September 26th, we expect all the stuff to be live streamed on NASA TV. So watch. Please join us and watch and follow along with us.
I know, and Aerospace is planning to be part of the party. We are going to set up some watch watching events, and it's going to be all over the news everywhere at aerospace and elsewhere, I'm sure. It's going to be in the news. So congratulations, and looking forward to a successful Dart mission.
Thank you. Thanks so much for having me.
Thank you. And I see from your bio that you like baseball and play your guitar. I love to hear you play sometime.
You say that now.
Okay, we are going to move forward to Madhu.
Oh, great.
Hi, Madhu. I think you have a very long bio here, so I'm going to skip it in the benefit of time. Maybe you can say a couple of words about yourself. You're a professor at USC here in Southern California. And I suggest you just take it away, say a few words about your academic and research activities, and looking forward to hear what you have to say today.
Okay, good. Can everybody hear me?
We can hear you loud and clear.
And are the slides coming up? Ken?
Now they are, yeah.
Oh, good. And so, you know, I have two, I have feet in two schools, the School of Engineering and the School of Architecture. And in the spring, I dealt with hardcore architects who are worried about the problems of the world. And in the fall, I teach a course called the Space Concept Synthesis Studio. We are thinking about ideas that are very, very young ideas. And let me share some slides about what we think we could be doing about opportunistic missions to take advantage of asteroids as they fly by close to us. As Nahum wants you all to know, USC has a very specific program in astronautical engineering. Don't confuse it with aerospace engineering. The curriculum is different. And it's a small program, but we are doing very well, attracting students from not just the United States, but more and more from all over the world. Now, what is within it is our studio. And the concept studio is really about one thing and one thing alone. Unbridled imagination, exercising your unbridled imagination and not really succumbing to requirements, documents, and other kinds of things that happen during engineering development. As you know, imagination is the thing that drives our species towards new horizons, new ways of thinking, new worldviews. And so we cherish it in academia as well as in the industry or at the agencies. So it is about from imagination follows creativity. And in all of our areas, including this topic that we call planetary defense, I think imagination and creativity is at the forefront of the design of missions. So we look at a range of possibilities and then winnow them down to what is really possible and practical. So in a few words, we would say that our studio is about what we would call pre-engineering, pre-PDR, you know, in engineering terminology. And it's a background activity. In fact, I should not be lecturing this to all of you because every day, every moment of our lives, we are thinking imaginatively about what to do and the choices we make. But it's only when we get narrowed down to our discipline and that we put on blinders and become very focused on aspects of engineering. The recent things that we've been discussing are about Artemis and Gateway project. I want all of you to take a look at the blasphemy that we we produce in school. But again, it is in the seeds of imagination that creativity is born, and we produce rich and wholesome ideas for our missions. Now, the history of me getting involved in planetary defense, I was always interested in all the things we do as a community. But in 2013, we did a project called Eden Shield. And I want you all to take a look at that to see the variety of ideas we threw out to suggest that, what are the possibilities and what can we do? So that led, that 2013 project led to I think my slides are a little bit screwed up here. That led to a team project. And in it, we thought that directed energy is one of the quick ways to mitigate an impactor, a bolide, that is on a terminal trajectory when you have weeks or months to mitigate it. Now, coming back to that studio, so we have interesting people come to our studio. Of course, if you see my cursor here, you can see our leader right here. And Buzz Aldrin is a friend of our studio. He comes in often, unannounced, and this is one of our gatherings. As you can see, we attract a lot more reviewers and guests than our students. And this, I believe, was, when was it, Nahum? 2019 or 2018, I think. But you'll see a very interesting group of people in our studio.
Yeah, it was an exciting event just to be in the presence of famous people.
All the people, I know, it's a very interesting time. So now let's get to a little bit of this heresy that I'm about to mention to you. Again, we don't have, all these ideas are at a qualitative level, which means that it is long before somebody thinks about putting some numbers to it and so on. But we know some things are happening right now. We are crowding our orbits with satellites, assets. Some of them have short duration longevity. Some others may last much longer. And most of the images you're seeing here are probably in the LEO and MEO segment. But look at the numbers. Look at the numbers of objects we are putting into the sky. It is astounding. And this has happened in the last few years. And we expect this to go further till somebody does something about it. And that is in another category, which we call orbital debris mitigation. We won't be studying that. So I just looked, I cannot do my courses without Google and Google Images. And it is amazing what Google puts out in terms of visuals that tell you what can happen, what we can do, and what is happening in the world today. I tell my students, there is a new generation of students coming up who don't go to university, but gain a lot of information from Wikipedia and a variety of other things, including open-aware lectures from the big schools. Anyhow, talking about visuals, this is a new one that came out. It tells you about the number of assets we have put into orbit. Currently, this is a 2022 slide, and I found it very interesting to look over. You must probably, you can look over, just look at the company name comes up, DoSoft. It tells you the number of nations that are directly involved in operating assets in orbit. And it doesn't take much to notice that the giants of satellite ops, manufacture, new missions is all in Congress in the United States of America. And then there are a few others, including Russia and China. The UK operates a lot of satellites, as you can see, and all of Europe too. But what it tells you is that there are a lot of assets out there, many of them most of them looking at planet Earth, and some, as Andy mentioned, are going out into space and doing magical things with asteroids. Another slide that I would love for all of you to see is if you Google graveyard orbit, the Wikipedia brings up a very interesting slide, which is a must for those in this group who are looking at orbits to know how things really move. I just got a screen grab here, but it's beautiful to see Kepler's laws enacted in real time in this particular animation that is on Wikipedia. Now it tells you that there are several satellites orbiting, and of importance perhaps is the graveyard orbit. What happens is that when satellites are decommissioned, end of life as you call them, it takes a lot of delta V, a lot of energy to fly them back and burn them up in the atmosphere. So conveniently or inconveniently, we push them, just give them a little energy to move them out to that little spot, a little bit outside of geosynchronous orbit. And there are a lot of these waiting there. Many of them are operationally viable, but unable to maintain their orbit status because of the depletion of fuel, or perhaps some failure of some equipment. Now, there's another Google page that is wonderful. And I know that Navum loves to talk about it. And Paul Church and others at the CNOS at JPL, and does a fantastic job updating what are the kind of objects which we call near Earth objects that are in close approaches. Over time, you notice that there are many objects flying our way, and we're getting better at looking at them and knowing that they're coming our way. So you can click on different things here. I did just to see what are the things coming at us in the next 60 days. I put down a nominal distance to say how far away is it coming towards us as the 0.05 AU. And you can do a lot of little things on these little tabs and get some interesting results. What you see here is that, as I mentioned to you, a lot of objects, near Earth objects, are coming our way, close to us in the narrow region between a few distances from the Earth-Moon distance, let's say 1 or 2 million miles. And so the question is, rather than spend a lot of time on these beautiful presentations that Andy did, which takes a year or so to approach your target, is there a way? This is a question to all of us. Is there a way to quickly look at some of these things coming toward us and gain some understanding, which otherwise take dedicated missions over a long period of time to investigate? So this is what we call a near Earth object intercept. And of course, God forbid, when they come into our skies, we see them as shooting stars, as Andy mentioned. And if it is big enough, if the rock is big enough, you get an event like Chelyabinsk, God forbid that happened. It happened over a populated area like New York. And so this is why planetary defense is important. It's vital to our civilization. So when we get close to, when objects get close to us, can we send something towards it at that time and investigate it as well? So a typical asteroid mission, as Andy put it beautifully, I did not know some of the details. It was beautiful to hear what Dr. Rivkin mentioned. Campaigns require a lot of time, and it is very elaborate. There are many payloads involved. I think, again, you saw that in Dr. Rivkin's slides. It takes time to arrive at the target, and of course, everything costs money. Asteroid missions cost money, so do other solar system missions. And so our idea, this particular question that I'm throwing out to all of you is, can we do better? When asteroids get closer to us, we can get some images. Many of them are very low resolution. And as Dr. Rivkin mentioned, even getting close on a planned mission, you have just a few minutes to catch something that's a few pixels across. And then perhaps as it gets closer, we get better images. Radar images can do this much for us, but can we do any better? And that is where we think we can do opportunistic missions. So what is the aim? Very specifically, or very simply put, can we get better images than what Goldstone radar can give us, and very quickly? So this idea is really about only those objects approaching close to us, 1 to 2 million kilometers, maybe 5 million kilometers from us. So right now, as you know, we have surveys going on that look at earlier surveys to pick out asteroids and so on, but I suspect those are for larger asteroids, even though we may pick up some smaller ones. But I'm thinking that for objects that are very small, we may still see them coming toward us or coming into our region of influence in a matter of months. And so we're wondering if we can use orbital assets already in place, doing other things, meant for other tasks. Can we engage them to do our bidding, which is to just get us better images and a few better a few better characteristics of these incoming objects? So the simple thing to do is use get a survey of all decommissioned orbital assets that are either in gravity orbit or elsewhere, and have an eye on them and match them up with these kinds of missions. What you do simply is attach a stage and fly them towards the target. And it may not take very long to do this, provided we have some of these lined up decommissioned assets, and we know what stages to put in them and dock with them and send them off on flight. As you know, the moon and the Earth, plane changes cost a lot in terms of delta V required for any kind of mission. So we have used the moon very cleverly in the past to make plane changes. And between the Earth and the moon, there are so many beautiful orbital dynamic changes we can make in a matter of weeks. So assuming that the mission is the entire mission is about 1 to 2 months long. Can we do this? That is, get enough delta V onto an existing asset and fly them towards the asteroid in an intercept mission. Again, as I saw in Andy's slides, things will happen very quickly in a matter of minutes to seconds. Can we imagine? And this particular idea is not optimum by any means of a regular, typical asteroid mission, but something is better than nothing. So what would the sequence of events be? First, we would acquire the target that we are about to fly to. 2-month notice, and Andy mentioned some wonderful departments that can do this for us, organizations. And then we do a quick trajectory analysis, find out the delta V requirements for an intercept. And then we go to a table of decommissioned assets and attach an interceptor stage and use the Earth-Moon flyby if we need to tweak the orbits a bit, and a fast flyby of this NEO. Get as much data as possible. Many of these assets in graveyard orbits, they have fantastic visual elements, payloads in them, optical, spectral, and so on. And all we need to do is get them going on their way. And there are some new techniques available to even include extending lifetime, not only in propulsion, but also in power. So these are things happening right now. That is the idea. That is pretty much the idea. Now, I want to remind you that once in a while we hear twinkles of interesting thoughts, one of which is from Nate Silver. All of you know Nate Silver, the guy who puts out the 538 bulletin that we constantly go to see how the polls are faring in different elections. He says something that I want you all to regurgitate on. There is a tendency in our planning to confuse the unfamiliar with the improbable. The contingency that you have not considered seriously looks strange. What looks strange is thought improbable. So improbable does not need to be considered seriously. It is a very dangerous thing we do as a species. And this is true for planetary defense. Everybody says this, and that is, what is the probability that we'll get hit? And as you saw in Dr. Rifkin's slides, one hit in a million years. Wait a minute, can that million years, one hit can be tomorrow? Well, I'm exaggerating, but we know that an object, a bolide, can come out of nowhere, particularly comets. We see them 6 months, eight months ahead of time. And we need to rethink how we think. And with that, I was thinking about, we have in our studio, we enjoy the idea of having catchy titles. And so last night I was thinking, what would I call this idea? I think we'd call it opera, opportunistic reconnaissance of asteroids. And as you can see, I got Charles Garnier's Paris opera there. There are some interesting thoughts, but we'll talk about that later. Anyhow, these are my little thoughts, Nahum and the rest of you. If you have some questions, I'm afraid to take them, but please.
Thank you, Madhu. Exciting as always. and interesting as always. I don't see any questions
Okay.
on the chat or the Q&A part, but I do have a comment, right, that I supported your students. Some of
Yes.
them actually came to aerospace, and I collaborated with some of them. They are truly brilliant students and well educated. So definitely you've done a good job in preparing them for the real world, Madhu. And the interesting part is that when you talk about mitigation of asteroid hazards, it's the big question: how close can we push the envelope to be able to address short warnings, right? Obviously, if we have a few decades, we have plenty of time to engage with the usual process, build, test, build a few, and so on and so forth. The question is, where is the limit? Is it 10 years, 5 years, 1 year, a day, a few minutes? That's the big question that is open. And I think it is connected with priorities and budgets, right? When a real threat is identified, surely it's going to rise in the order of priorities to maybe near the top, and it will get the resources that it deserves. But if it is once in a few thousands of years, it gets averaged, and the risk tomorrow seems small, even though the consequences could be really, really bad, but the risk is perceived to be very small.
That's right.
And this drives the action behind what to do and what not to do.
And I know, Nahum, that your group, at least since we had the 2015 exercise at the Space University, aerospace has been doing short-term strategies. And in the last two gatherings of the mini conference that can put us all in together, I saw some of the recent things that Aero has been doing to mitigate short-term threats. Yeah.
And I think this is an area of attention that is now getting more, that is being addressed by NASA from the last talks that I've seen. And they're definitely putting some attention to extremely short warning situations where we didn't catch them in deep space. What can we do when they're just about to enter through the atmosphere? So there are several people who are doing that. Phil Lubin of Santa Barbara is engaged with that. And I think, is it Lawrence Livermore or NASA Ames, one of those centers are engaged with those type of studies. So I think there is some attention that is given to that. And with that, Madhu, thank you so much. I think we are going to take a lunch break now and self-transport to the UCLA Meteorite Gallery for a tour of the lab, a few talks by the UCLA scientists, Professor McKeegan and Alan Rubin, with Q&A. Everybody is welcome to join us in to the in-person part of the event. And at the late part of the afternoon, we'll hear a talk about a scientific mission to asteroid Psyche by a couple of my colleagues at Aerospace, and about STEM activities that Aerospace is engaged with to inspire the next generation of scientists and engineers that maybe one day will end up in your class, Madhu. And we'll hear about the movie Asteroid Hunters that is going to be presented by the producer himself in the afternoon with maybe a quick shot. And the movie itself is trying to show up in the theaters at the end of this month. So go to the Science Center, IMAX, and watch the Asteroid Hunters movie, and you might recognize somebody there.
Yeah, you know, talking about movies, Nahum, I hope you watched the Don't Look Up movie, which we did. And, you know, it was tongue-in-cheek for most of the activities that were presented there. But I recommend, and I think our community recommends, please look up. And also I feel strongly, you know, I'm not a Facebook kind of guy, at least I wasn't. And then I Googled amateur astronomers over the last year. There are thousands of people with telescopes looking at our skies, Nahum. And it's my thinking that if we do this, we enhance our abilities to look at things coming at us. And even now, many of the asteroids are still, though we automate the system, still many of the asteroids are picked up by amateur astronomers, and that is fascinating to me.
It is. It is. I think it's a community type of effort, citizen scientists project, and I totally support your idea. I think it is something that is being implemented occasionally by NASA and others to do a citizen scientist project where people participate in certain scientific activities. And I think for planetary defense, everybody is welcome to join the community of
That's
planetary defenders. So I think with that, I thank you very much, Madhu. Are you going to join us in the afternoon, or we'll see?
I'm sorry, I won't. You know, I would love to come and see the meteorite collection, but I'll have to do this another time. No, hope all of you enjoy lunch and the event following, and the rest of the talks do appear very, very interesting. And I have to thank Ken, the incoming section head for AIAA Los Angeles, Las Vegas, for the amount of work he does to bring all these beautiful events together. Thank you to all of you. Thank you, Noam, and thank you, Ken.
You're welcome. Can you hear
Thank
me?
you, Madhu. Congratulations, Ken. And we'll see you in the afternoon. Ken, would you like to give a few instructions and concluding remarks for the morning session?
Oh, we put the Professor McKeegan and I will put the sign in front of geology. So if you drive and park at parking structure 2, you should see an AIAA banner. Just by the way, if the banner somehow falls down, please, straighten it up because it could be windy. So you go, enter the building. I think Professor McKeegan put the sign there. You can take the stairway, go to the 3rd floor, or you keep going to almost to the end and take the last elevator because 2 of the elevators were not working. So you go to 3rd floor, and you basically turn right and follow the sign. Or maybe Professor.
Hi, I think you can hear me without that. We've got to work on the echo in here. But anyway, what's
the
question?
direction. If people want to drive or come here, do you have a quick direction for them?
Look on the website. I mean, we'll come up to where you're coming from.
So everybody is going to be coming from different areas, but everybody can put the GPS. I think in the invite, there is the address for the Meteorite Gallery, and you just park in parking lot number 2, go to the geology building and look for room 3853, right? Is this the correct room number?
You have to go up 2 floors. Okay, and you can walk, which is good for exercise, but if people have trouble with that, the closest elevators are not working, so they have to keep going down the corridor to another elevator and take it to the 3rd floor. We're going to put out some sign now. Unfortunately, the elevator is still not functioning.
Thank you very much, Professor McKeegan, and see you all in the afternoon at the Meteorite Gallery. Looking forward to an exciting tour and talks.
Okay, you will see the signs. Ken has put out those AIAA sign, and we have the Meteorite Gallery sign, so you will find the place, I think.
Yeah, I think it's very easy to find. The address is on the invite for this presentation. And also, if you just Google the UCLA Meteorite Galleries, the directions are going to be very clear. You just put it on your GPS and let your car take you there.
Okay, great.
Thank you all.
Thank you.
Thank you, Madhu, again, and
Okay.
see you soon.
Bye.
Okay.
Yeah. Monica
now.
is actually here.
What, Ken?